All right. So we're going to be drawing 1, 2, 3, 4, 5, 6 VT graphs. So that'll go down the left side of the page, and then we will put some stuff with each graph. And each graph will look like this. It'll have a vertical bar, and then halfway a horizontal bar, just so that we can see sort of the positive and the negative. And these, of course, are VT graphs. And we're going to do 6 of these. So if you got a copy paste tool, you'd be happy. Yeah. Yeah, down like this. That's a T. 6 of those, yep. Down the page. So I only got room for 4, so you need 2 more. Okay, so as soon as you guys got 6 of these, we'll start. Shh. Elgin, maybe you'll sit over there, man. Okay. Alright. Okay. So we're gonna, if you had another color, that would be good. And we'll draw in the VT graphs now. So let's draw in a VT graph like this. And just another color just helps with understanding like where the graph lines are versus what the actual graph is. All right. So this VT graph, remember, we're not talking about DT, we're talking about VT. So as time goes on, the velocity is remaining constant. So what does that tell us? If it's a constant velocity time graph, then we know that acceleration is 0. Because the slope of a horizontal line is 0. Okay, we know that, we talked about this yesterday, the slope of a VT graph is acceleration. Also, the graph lies above the x-axis, so we're talking about which direction for this velocity. And we'll talk left and right, one-dimensional. So this object is traveling to the right. Okay, because of the positive v. Okay. The ticker tape would look like this. Equidistant points. With the motion obviously to the right. So The ticker tape is a way that in physics you can measure um, like position or velocity. Okay, the ticker tape is the position. Okay, so this is the position, not the velocity. The ticker tape is the position. So here, 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 and these would happen at some time intervals, and usually the ticker tape is set to like 0.1 seconds because you know it happens quite quickly. So every 0.1 of a second, okay, so this is position and time, and we drew a few of these yesterday, position, time, and I'm not going to draw it every time, the position and time, but the ticker tape shows position and time. Okay, so let's draw the exact same thing, but this time negative. So horizontal, negative. So again, we have some similarities. We have a constant velocity, therefore A is 0. But it's going to be traveling leftward. Because of the negative velocity. Now when you draw your ticker tape, or if you were just like watching a car drive, why isn't this working? If you were just watching a car drive over time, you'd see it there, then you'd see it there, then you'd see it there, then you'd see it there, as the motion was going this way. So you could imagine these dots as a car every second if you'd want. Think of it as a car. This is after 1 second, this is after 2 seconds, this is after 3 seconds, and this is after 4 seconds. And if it's got a constant velocity, these positions will be equally distant apart. Again, this is position here. Position versus time of a car. Going to the left this time. Equidistant. Okay, so now let's amp it up a bit. Let's go with a line starting at the origin with a positive slope above the x-axis. Okay, so this time it's not constant. The velocity is not constant. It is linear. Okay? Linear and increasing. Okay? Above, it's also linear, but it's constant. Now we're linear and we're increasing. Okay? So with this positive slope, we know that A is not 0. It is accelerating. Okay? So a positive slope means that the acceleration is positive. Positive slope, positive acceleration. And this is the symbols for positive. Greater than 0 is the symbol for positive. Now the velocity, which direction are we headed? Positive, because we're above the x-axis. This is positive velocity. So what would a diagram look like of a car driving? We are headed to the right, and the acceleration is positive. So we are doing rightward acceleration. So how does the dot diagram look like? Imagine a car driving to the right. It's getting faster. Do you agree? As the velocity rises, time is going on. Your velocity is increasing as time goes on, so you're getting faster. You start off slow, and you start to get faster. This is motion to the right. So this would be like every dot, say 1 second, a car traveling to the right. 1 second, 2 seconds, you're getting farther apart between points. Now we'll draw a VT graph angled down, but in the positive region, like this. So now you have a negative slope contrasted with above, which had a positive slope. So now we have a negative slope, which means our acceleration is negative. So negative acceleration has a word. It's deceleration. Okay, so it means the same thing. Negative acceleration and deceleration. So as time goes on to the right, you can look at my pointer. As time moves on to the right, velocity is decreasing. So you must be slowing down, which means you're undergoing negative acceleration, which is deceleration. Okay. Again, though, we are traveling to the right. You're still traveling to the right, but you're decelerating. So what would that look like with this left acceleration, the negative acceleration? An acceleration is a vector. So the acceleration vector is pointing left. So I'll stand up. You're traveling to the right, but the acceleration is to the left. That's like driving a car and throwing on the brakes.
Tori, can Miss Canna please come to the office? Tori, can Miss Canna please come to the office?
So imagine you're driving in a car, excuse me, you're driving in a car and you're going to the right. If you throw on the brakes, you're accelerating to the left. So you slow down. If you're driving in a car to the right and you hit the gas pedal, you are accelerating to the right, so your acceleration vector is also to the right. You would speed up. Does that make sense? Okay, so we're traveling to the right. The motion is this way, but we're slowing down. So it's like the opposite of this diagram. Here you're traveling quite fast, and then, come on, Dot. And then they start to get closer. And then it gets even closer. And then by next thing you know, you've stopped. Because, I'll use my pointer, if you still haven't quite grasped this, up here on the graph, up here, your velocity on the graph is quite high. Do you agree? So you're going fast. And then over here, your velocity is closer to 0, so you're going slow. So as time goes on, and these, it's like a picture. It's like a snapshot in time. Here's at 1 second. Here's at 2 seconds. Here's at 3. Here's at 4. Here's at 5. So the pictures of this dot are taken at the same time interval, but the distances between them are getting smaller. So you must be slowing down to a stop. Okay, 2 more to go. Okay, so it's basically the exact same 2 graphs, but this time in the negative region. Need a line tool. So this one. Let's try to think about what's happening here. And I'll just zoom in because there's only 2. Alright. So what's happening with this? You're starting off with quite a high velocity in the negative direction, but as time goes on, your velocity is approaching 0. So what is happening? You're headed left, and you're slowing down. That's what this indicates. Because you're in this region, the velocities are negative, you're headed left. As you approach the x-axis, the magnitude is decreasing from a high value to a low value. So you're slowing down in the left direction. Let me write those words down. Positive slope acceleration positive, and this might confuse you at first. Left velocity, because it's negative. Now, let's try to think about why you're slowing down. The positive slope tells me that the acceleration is positive. So if I'm traveling left, but my acceleration is positive, they oppose each other. So you slow down. And the diagram for that would look like motion to the left, and you're slowing down. So at first they're quite far away, and then they start to, until you stop. And this is just a car at regular time intervals. And now the last one for these VT graphs, in this one, slowing down. Slowing down, yeah. Motion to the left, acceleration to the right. And the way that we do this in physics, and I'm going to talk about this tomorrow as well, but oh my gosh, pen tool, come on. The velocity vector is to the left, and the acceleration vector is to the right. So since they oppose each other, you're slowing down. When the velocity vector and the acceleration vector are in the same direction, you speed up. So let's do the last one. And this would be a sloping line away from the x-axis in the negative region. Okay, so as time goes on this graph, as time goes on, you're getting farther and farther away from 0. So the magnitude is getting larger, so you must be speeding up. The slope is negative, so your acceleration vector is also negative. And since we're in the negative region for v, you're also traveling left, because the negative velocity values. So I'll stand up again and I'll show you. On this graph, the values are below the x-axis, so we're traveling left. The slope is down to the right, so the slope is negative, so that slope of a VT is acceleration, so acceleration is negative. So the vector for acceleration and the vector for velocity are in the same direction, so you must be speeding up. You're speeding up to the left. Correct. Like to the other ones we talked about? Yeah. So speeding up to the left means you start off slow, and then they start to get farther apart. So once this is done, I just got one more thing to add. We'll go back to the previous page. Just let me know when you guys are good. Chris, you okay? All right. Okay, let's go back here. Let's just make a couple notes on these. So for the first two graphs, you're not speeding up or down in the first two graphs. So that would cover these two. For the third one, you're speeding up. And for the fourth one, you're speeding down. Speeding up and speeding down. And the last two, motion is to the left, so we are speeding down on the fifth graph and speeding up on the last graph. Okay, well, last piece for graphs. Okay, so this is VT area. This one, you'll just have 3 graphs. So let's just do one at a time. VT graph. Drawing a line, a straight line. And let's say 2, 4, 6. Like that. And we'll say on the y-axis, I don't know, 10, 20, 30. 10, 20, 30. All right, so I mismentioned this briefly, but area under the graph for a VT, and I'll color that differently. Area under a graph represents displacement, and it's the VT graph. Okay, area under an AT graph is different. Okay, so this is area under a VT graph. So the displacement, not the distance, right, with the vector arrow symbol, displacement during the first 6 seconds will be the area of a rectangle in this case. Area of a rectangle is length times width, and in this case the length is t and the width is v. However you want to slice it, it's vt. And you guys know that formula. D equals vt, you already know that. So that should make sense. Why is d equal to vt? Well, look at the graph. And remember, we talked about this formula d equals vt, and what did I say about this formula? When is it valid? Uniform motion. And if you look at the velocity, is the velocity changing on this graph? No. So this formula valid for uniform motion. 2 more, you guys. All right, so let's draw sloping VT. Color it in. All right, let's just say this is, doesn't matter, like 40, 30, 20. 30, 20. Oh my gosh. So again, it's VT graphs. Let's say 2 and 4. Let's do that. So for this graph, the displacement during the first 4 seconds, 0 to 4, and again, this could be any time interval you like. You just have to draw in the shape and color it in, find the area. Well, this is not a rectangle. This is a triangle. Area of a triangle, base times height, and we're going to divide by 2. So that's the area of a triangle. The base is time. The height is v. So we basically have vt over 2. But we have to be careful about this v. This is actually a delta v. Sorry, not delta v. Delta v is change. This is a sum. So just keep it vt and we'll highlight it. Because the height of the graph, I'll use my pointer instead of using my hand. If we look at this graph, what's the height of this line? Well, it's 0 plus 30. It just happened to be nice because it starts at 0, so you could just say the height is 30. But like, what if you were doing a different part of it? Okay, so the height is 0 plus 30. Or 30 minus 0. However you want to slice it up. And then when we get our formula sheets, you'll have this formula. Okay, and this is for non-uniform motion. You'll get this formula. It'll be on your formula sheet. The V final, I'll use my pointer. I don't know why I get over here all the time. So VF, where's VF? It's right here. This is the final velocity. It's 0. And VI is 30. So 30 plus 0, this is your height. And the reason we have a divide by 2 is because it's a triangle. Times the base, which is 4 seconds. That's your time. So base times height divided by 2. And then we only have one other situation. Is when you have like a section of the graph, and I'll have to give you another diagram. And this is it for the notes, okay? So bear with me. Only got one more diagram to draw. I know you guys are here all day probably taking notes. It's probably tough. Okay, again, VT. And let's just go 10, 20, 30, 40, and 50. Let's draw a sloping line to the right this time. And your VT graphs will never be curved. All right. So let's imagine that we're going from 2 seconds to 5 seconds. So we want this area. Okay? Now what shape is this? What shape is that? Math people, what shape is that? Good, trapezoid. And who's got the trapezoid area formula memorized? Nobody, right? That's crazy. Anyways, displacement during 2 to 5 seconds will be the area of a trapezoid. The other alternative is to do what? If you didn't know the formula for a trapezoid, chop it good. Very nice. You just do a triangle plus a rectangle. That will also work. Okay? So if you're doing a question like this, an alternative would be to do like area 1 and area 2 and just add them. That's definitely a good choice. And then the area of a trapezoid is 1/2 the base times height 1 plus height 2. So the base here would be time, and height 1 would be, this is like your VI, and this is like your VF. So height 1, I'll highlight these for you. Height 1 is this VI, and height 2 is your VF. Also highlighting the base as time, and then you'd get the area of a trapezoid. And this is analogous to what we had on the previous page. It's the exact same formula. It's just this VF plus VI over 2 times T. It's on your formula sheet. Same formula. It'll work. Okay? So that's it for the notes for 2.1. Okay? So that's end of 2.1. Okay, so you have your, I'll stop the video.